Parallel circuits. In this video you will learn what a parallel circuit is, and you'll learn how to calculate the various quantities within a parallel circuit, such as the voltage drops and the currents at various locations and the equivalent resistance in parallel. You'll also see where parallel circuits are used and how parallel circuits are similar and also how they're different from series circuits. Remember, when you see the pause video indicator, to pause the video and take great notes. Let's start by looking at the structure of a parallel circuit and seeing how it's different than a series circuit. In a series circuit, we just had one loop or one path. In this parallel circuit, we have multiple paths. The electrons get a choice. When they come along here, they can either go through resistor 1 and back to the battery, or they can go here and go through resistor 2 and go back to the battery. So there are multiple paths, and you could have a third resistor or a third component and more. It doesn't have to be just two. It could be 3 or 4 or 5 different components here. So that's the main difference between a series and parallel circuit, and these components look like they are in parallel with each other, side by side. Notice that in a parallel circuit, because of its structural difference, now when a bulb goes out or burns out and opens circuits, the electrons have another opportunity to still make it back to the battery. This bulb will not turn off, it'll stay lit. And this is why your house is wired in parallel, is because the different outlets can operate independently of one another. Let's take a look at a very important concept with parallel circuits, and that is the idea that voltage is the same across all the components in a parallel circuit. And this is why. Here's our source, and if we look right here, this good conductor connects to the top of resistor 1, and it doesn't take any work to move the charge right to here. All the work is done to push the charge and pull the charge through the resistor. And then it doesn't take any work to move the charge back. So there's no loss in voltage, there's no drop in voltage to here, and then there's also no drop in voltage all the way back. So all 12 volts of that potential difference show across resistor 1 right here. So the voltage across resistor 1 is 12 volts. Notice also that that's true for resistor 2, that we just have a good conductor all the way to here, and then we have a good conductor all the way back. So no work per charge is done to move the charges to here, and no work per charge is done to move the charges back to the battery. So all 12 volts appears also across R2. So anywhere across any component in a parallel circuit, the voltage is the same. And we can have R3 and R4, and it would still be 12 volts across all of those components. And again, this is why your house is wired in parallel, so that each component, when you plug into an outlet, will experience the same voltage. In a house, though, it's not 12 volts, it would be 120 volts. This is probably one of the most important ideas in parallel circuits, that voltage is the same. So let's start out analyzing a parallel circuit, since we know a couple of things about them, and mainly that the voltage is the same across each of these resistors, and therefore we can go about trying to calculate all the currents in a particular parallel circuit. So we have our parallel circuit, and we have our two different resistances here, a 3 ohm resistor and a 6 ohm resistor. And if we want to find these two currents, we can do that using Ohm's law, because the voltage, the 12 volts, is going to appear across both of these resistors. So we know the voltage drop across resistor 1 is 12 volts, and we know that it has a resistance of 3 ohms. So the current in I1, the current here in resistor 1 is I1, and so that's, by Ohm's law, I equals V over R. So the voltage across resistor 1 divided by the resistance of resistor 1, 12 volts divided by 3 ohms, is 4 amperes. And likewise over here with resistor 2, the current through resistor 2 is equal to the voltage across resistor 2 divided by resistance of resistor 2. So 12 volts divided by 6 ohms is 2 amperes. Now this should make some pretty good sense here, that since the voltage is the same and resistor 1 is half the value of resistor 2, that we should get twice as much current flowing in this branch as we get in this branch. And these are called branches, by the way, if you noted that earlier, and these are called nodes where the branches connect together. So at this node, some of the current's going to flow this way and some of the current's going to flow this way. Again, twice as much current flows through resistor 1 because it is half the resistance. Half the current flows through resistor 2 because it's twice the resistance. Now, another thing to note is that when the current comes in here, it splits, like a river splits into two tributaries here and here. This river comes in, this river of current, some is going to flow this way and some will flow that way. Well, 4 amps flows this way and 2 amps flows that way. So it should make sense that in order to feed 4 amps and 2 amps, we better have had 6 amperes flowing in. And then when the 4 amperes and the 2 amperes come back together here, they will recombine and we'd have 6 amperes going back to the battery, which makes sense because with conservation of charge here, whatever charge goes out, we need to have coming back in. And so to find the total current in a parallel circuit, you just add up all the branch currents. 4 plus 2 is 6 amperes. Why don't you try one and see how you do just from that previous example. So we want to know what current would flow if we have a 6-volt battery wired in parallel with 8 ohm resistor and a 2 ohm resistor. Draw your circuit, give it a shot, and let's see how you did. Well, how did it go here? Remember that the voltage is the same, and so the 6 volts is going to appear across both resistances, and since we have the resistance, we can use Ohm's law to find the different currents. And hopefully you got 0.75 amps for the 8 ohms and 3 amps for the 2 ohms. And proportionally this should make sense. This is 4 times more resistive this way than it is this way. And so we should have 4 times as much current flowing in our 2 here as we have flowing in R1, and it looks like that worked out. And we know that the total current coming in has to split and go into both of these, and so to find that total current we can add up both of these currents and we get 3.75 amperes. It's kind of like opening up a lane on a freeway, and so we'll talk about that next, how we're going to get more and more current. If you see here, when you add resistors in parallel, it's kind of opposite what you do in a series circuit. When we added resistors in series, the resistance got greater and greater. But when we add resistors in parallel, the total resistance is getting smaller and the total current is getting greater. More on that next. As I was just saying, resistance works a little bit differently in parallel than it did in series. So let's take a look at how we can find the equivalent or total resistance in a parallel circuit. And like I was just saying, when we add resistors in a parallel circuit, what we find out is that the current actually increases, and it does because we've opened up new pathways. The push and pull, the voltage stays the same, so if there's another pathway for the current to flow, we're going to actually get more current flowing overall. So in this particular example, if we just had this circuit, this simple circuit, we'd have 4 amperes flowing, and then when we added this other resistor, we'd gain another 2 amperes because we'd have another path. It's like opening up a lane on a freeway. And so we'd have another opportunity for electrons to flow. With the same push and pull, we get more current flowing. Well, since we've increased the current, the total resistance has gone down. the equivalent resistance should reduce when we add more and more resistors. And that's what happens. If we find the resistance, equivalent resistance using Ohm's law, the total resistance is the total voltage divided by the total current. Since the total current is 4 plus 2 amperes is 6 amperes, 12 volts divided by 6 amperes is 2 ohms. Notice that the equivalent resistance that the battery feels is attached to it is less than either of these resistors. It is less than either one because they both are allowing more current to flow. Now there's another way you can find total or equivalent resistance in a parallel circuit, and that's when you don't have a source. And when you don't have a source, you can't use Ohm's law. And so what you do is you use this equation where you have, it's called products over the sums. You have R1 times R2 all divided by R1 plus R2. So it's kind of a dividing effect here, and that's why the equivalent resistance is going to be reduced when you use this equation. So if we have these two resistances and we plug them in, our 3 ohms and our 6 ohms again, 3 times 6 is 18, and ohms times ohms is ohms squared. So 18 ohms squared divided by 3 plus 6 is 9 ohms gives us 2 ohms. Again, this is the equation you would use when you don't know the source. So why don't you give a try with that interesting equation. You have a 20 ohm resistor in parallel with a 100 ohm resistor. What is the equivalent resistance? Well, hopefully you were successful, and hopefully you found the equivalent resistance to be 16.7 ohms. You can pause the video and check out your work here. But notice that this 16.7 ohms is less than the smallest value. Again, if I disconnected this 100 ohms, you'd have 20 ohms. And when I connected the 100 ohms, it would allow more current to flow that way in addition to what was flowing this way, since they have the same voltage. And that's going to cause a reduction in overall resistance. Let's quickly do an overall parallel circuit. Here is our circuit. And here's what we know. We know we have a 120 volt voltage source, and that voltage will be the same across all the components here. We have a 40 ohm resistor, and we know that the input current is 10 amperes, but we don't know what resistor 2 is. So let's go about trying to solve this particular circuit. The first thing that we're going to do is, since we know there's 120 volts across each of these resistors, and I know the resistance of resistor 1, I'm going to find this current, I1. So use Ohm's law to find that current is 3 amperes flowing in this branch. Now, I know there's 10 amperes coming in, and 3 amperes goes this way, so I can use this idea that the total current is the sum of both of these currents. And so 10, if 3 goes this way, I must have 7 flowing this way. And that's what I receive by doing a little bit of algebra here, but also just doing it intuitively. And that's how I could find the current in branch 2. Wow, well, if I know the current here is 7 amperes and I know what the voltage is across, I can find out what that resistance is, what R2 is. So that's what we're going to do on the next slide. So finding the resistance here, since I know this is 120 volts and 7 amps is flowing through it, R2 is equal to V2 divided by I2. And so 120 divided by 7 is 17 ohms right here. And I can also find the total resistance in this circuit, because I can take my 120 volts total voltage here and divide by 10 amps of total current, and I could get 12 ohms as the equivalent resistance in the circuit. Wow! That's how you can use your knowledge to solve for various things in a parallel circuit. Wow, that was a lot. And Scratch's parting idea? And good luck charting your way through that parallel universe as you strive for continuous improvement.